No passado a gente fez um evento.
Isso. Tá joia. Okay, so the second speaker of the morning, we have one extra speaker in the afternoon. So it's Reinaldo is the one who has to travel the east from UNICID to here. UNICID is the closest university to this. So we all, so I think this is your first time here, and so the spirit of this meeting is to gather the San Paulo community working in, say, gravity in all scales, from cosmology to planets. And I guess you are on the galactic scale. And please tell us all about it.
All right, thank you.
Now, 50, 55, 1 hour.
All right, terrific. Thank you very much, Reinaldo, for the day. It's quite a pleasure to be here today. It's a different kind of audience that I'm used to present this work. So I imagine most here are physicists, right? Any other physicists?
Well, maybe.
Yeah, exactly. So
The distinction is blurred.
yeah, it is. It's becoming more and more. Yeah. So I'll try not to bother you with the details, the gory detail, but if you have a question later, I can answer that. But I hope not. All right. So this is a study. Actually, this is a project we started 4 years ago when we thought about galaxy evolution. That's the main subject, galaxy evolution. And what is important for galaxy evolution? What we are trying to answer, what is the big question we have? That's the group of people that we got together. Igor Kolesnikov is the guy who finished his PhD recently. Victor Sampaio is finishing his PhD right now with me. Yes, evidently is an undergrad student, just starting to work with us. And Chris Gonzalez is the kind of expert in galaxy morphology. He made his career in galaxy morphology. You may think that, especially based on the first talk that I saw, that morphology of galaxy morphology is something like not related to physics at all. Right? It's just looking at something like when you look at an image of a cat and a dog, and you want to distinguish those things. And that's what I'm trying to do here. And I'll try to show you that although it sounds bizarre, but morphology is very deeply linked to galaxy formation and galaxy evolution. And the question is, how do we make this in context with cosmology? Because cosmology today seems like, unless you work with the cosmic microwave background or something related, you're not doing cosmology. And actually, you can do cosmology even with morphology. Very good that I have a brief something. My voice is just going on. Okay. So this is just an outline. I'll briefly tell you, what galaxy evolution is of low redshift, especially in the morphology density relation. And then I'll talk about the visual classification and the need for unsupervised classification. Most of the work we have doing so far is essentially visual estimate. And you can imagine how difficult it is, especially when you go to high redshift, right? So it is difficult. When you see galaxies nearby, it sounds easy to separate them in spirals and ellipses, but when you move out redshift 3 or even 2 or 1 and go into redshift 9 or so, it gets really work. Then I'll describe this new number metric system, SAIFR, that we call SAIFR. There is another system which is very traditional in cosmology, or at least in extragalactic research, which is the CAS system. I'll come back to this later, but just to put in perspective, CAS means concentration, and symmetry, and smoothness. 3 parameters that we believe they separate the early type galaxies and late type galaxies quite well. That's not really sure, but I will show exactly how that looks. And then, how SAIFR package that we wrote works at low redshift. We're going to apply SAIFR to candles. This is stated now to 0.2 to 2.4, moving out in redshift. Actually, moving in redshift is very misleading. I'll come back to this. Actually, we should talk about the look back time. That's much more meaningful. Because redshift, there's no cosmology in redshift. Redshift, as the name says, you see the lines of the spectrum moving to the red. the way you translate redshift to distance or time, then you need that cosmological model, right? So we got to be careful with this. But most works, they just refer to, redshift regimes. Let's not do something different.
Okay. Are you telling us that you are so precise that you care about different cosmological modeling affecting the time distance?
Not really, not really. It's just I'll come back to this. It's just when you show, for instance, the look-back time versus redshift, it's not a linear relation, right?
Okay.
It's something that goes up and just flats out. So when we say, let's look at the redshift regime between 3 and 8, it sounds like a lot. In time, it means 1.5 gigayears, which is roughly less than 10% of the age of the universe. So it is misleading when we talk about, ranges in redshift. We should be talking about the ranges in look-back time. And then, as it was there, I will dive into the very primordial. That's the basic fundamental question. What is the universe made of? When we look at nearby, and this is just describing what we see nearby, we have the sequence, the Hubble sequence, which shows, this doesn't work, right? Yeah, this one. Okay, so basically, this doesn't mean that the galaxies are moving, in this spherical diagram. It's just a way to show, what morphology is to better nearby universe. But then you have the early type galaxies, this is one component, not much star formation going on. You have an intermediate type, doesn't matter much. And then you have the type of spiral galaxies, ones which are barred spirals, and the normal spirals. Those are the typical things that we are used to in the nearby universe. Imagine that even in low redshift regime, there are things which are compact, which doesn't say much. Compact out there. There are dwarf galaxies. Peculiar means exactly whatever you want, right? It's not a spiral, if it's not a elliptical, it is peculiar. What is peculiar? We don't know. And then there is AGN, so there is a bright spot right in the center of the galaxy. That's the picture we have. And now I want to, call your attention to the fact that while the cosmic microwave background, the observation of it, can give a very precise way of estimating the primordial list of populations, small scale astrophysics is the bottleneck to get a robust theory for galaxy formation and evolution. Because then you have dissipation, and dissipation is a nightmare in astrophysics. Dissipation means you have a cool gas and cool with the gas make stars. But then you ask yourself, making stars, at what rate? Galaxies are different. And it depends if the galaxy has, cold flow falling into the galaxy. And the galaxy might be in the overall field where the density is quite low, or in the cluster where there is hot gas. So a galaxy may lose the content, and then the galaxy is quenched. As you can see, it becomes very complex in the picture, and that's why it's so difficult to have all this. Yeah, go ahead.
I have the curiosity actually.
Right.
I always had it, so this is interesting. The Hubble sequence. So suppose that 100 billion years from now, we don't have any mergers anymore. Nothing. Galaxies are there.
In the future,
In the future, yeah, not in the past. Where, what is the final state of a galaxy there? Let's say if you just look at gas, even stars, even if they are dead stars, where will be sitting there? What is the final the ground state for evolution of a system such as a galaxy? Is it some kind of a spiral? Is it an elliptical? Where is it? What is it?
I'll probably be able to answer that question probably like this. At the end of the talk,
Okay.
and then you understand why.
All right.
Because although you are asking for the future, maybe the answer is in the past.
Yeah.
When it gets very close to the point where we start making galaxies, maybe the answer is right there. Because there is a competition. I wasn't planning to say this right now, but I can tell you. There is a competition between the angular momentum of the primordial galaxies and the merger rate. So at a certain redshift, even at the very first redshift of the galaxy forming, you can imagine, which one is winning, right? Is the merger rate or the torque which induces angular momentum and make rotation of galaxies? Which means that's why most people involved in this kind of work, moving to high redshift, they want to show that there is a high frequency disks at the very high redshift. It's a bias that we have in our brain.
Yeah,
Most
so that
people-
connects to other questions I had, so I'll wait for the time end of your talk.
Yeah. You see. All right, so, just to elaborate a little bit more what I mean by galaxy evolution and why this is so important and why morphology becomes a fundamental issue. Here it is, probably you guys know that there is a HR diagram for stars, which means tell me what the mass of the star is, and the HR diagram will tell you exactly how the star moves around. Okay, it's a 1 solar mass, 10 solar mass, 100 solar mass. In the HR diagram, which is the basis of the stellar evolution theory, will tell you exactly how it goes. This is the equivalent for galaxies. So we call the main sequence diagram, which shows the star formation rate versus the stellar mass. And these two are two environments, cluster of galaxies and field. Field means here, it's a very vague kind of definition, a place where you don't have too many galaxies. The place is quite low. But I want to call your attention to here is we find 3 different phases of the main sequence diagram. The blue clouds, the blue clouds that have a high star formation rate. And then there is an intermediate one, and maybe a passage of galaxy from being blue cloud to red sequence, that was stands for RS. And then this red line here says systems that we say quenchant. Quenchant is, again, you guys, you hear me a lot saying this, is also quite a vague, because I would put this red line over here or over here. There's no precise way of saying, but quenchant means exhausted all the gas in the galaxy. So we don't have gas anymore. There's no precise way of saying this. So instead of saying it's a quenching, because quenching means the galaxy is losing the gas, not making stars. If you lose gas, you don't make stars. But then comes another question. You say, when you lose gas and you don't make stars, which one go first? The morphology change or the stellar population change? Because the stellar population is very sensitive to the amount of gas you have available to make stars, right? So, but it's not that the galaxy will lose the gas overnight. It doesn't happen like this.
But then stars evolve, they blow up, and they reset. Then there is some gas.
The massive ones, the massive ones will do it. The low mass stars, they will take a while to evolve, and they return the gas to the recycle mechanism, say, not very efficiently, right? So if you want to have much more gas, has to be through the high mass, and the high mass you don't have too many high mass stars in the galaxy. The majority of our galaxy, for instance, is around 1 solar mass, just like our sun dominates the population. So, but this is just to show you exactly the way we interpret how the galaxy evolves. So, if a galaxy is here in the blue cloud, forming stars a lot, and then goes into the cluster and sees the hot gas. The hot gas evaporates the gas from the galaxy, and then star formation goes down. And essentially the stellar mass doesn't change much because you didn't increase the stellar mass, right? This is a simplistic way of seeing exactly how a galaxy evolved in this diagram.
By the way, Reinaldo, is this data or is this simulation?
Is this data? No, I don't play with simulation. No. No, it's just like saying this is physics in the garage. You have to get dirty, right? No, but I will show you that there are some simulations of the problem. So in here, I show here's the formation rate. This is T-type. T-type is a parameter, essentially measuring the morphology. Low T-type, less than 0 means early-type galaxies, and greater than 0 means late-type galaxies, spirals. And then you see exactly, how it goes. The same diagram, you can look at star formation rate and morphology. There are some similarities in the behavior of those. Although I'm not saying that, the T-type, the morphological parameter, is reflecting star formation rate. It's just the way that galaxies evolve. And here I show the projected phase space. You guys are more, into the phase space where you see, the momentum versus the coordinated Q parameter. It's not the same thing here. What we call the projected phase space, the velocity is the peculiar velocity of the galaxy divided by the velocity dispersion of the cluster in total. And this is a function of the cluster center distance. And this is 1 Vira radius. So look at this. We see blue cloud, green valley, and red sequence, as I said before. But now in terms of different ranges of stellar mass. So what we see here, you see the red colors are,
This is galactic mass, the mass of the galaxy.
that's the stellar mass.
What can be 10 to the
It's a stellar mass of the galaxy.
stellar mass of the
Stellar mass.
Yeah, so, okay, so,
Stellar mass goes essentially from 10 to the 8, 10 to the 11. Well,
yeah, true.
that was the guess.
No, I was thinking the stellar mass is the mass of a star, no?
No,
The
no,
mass
no,
of the
no.
galaxy in units of.
These are galaxies. These are galaxies. They are made of stars, but they are galaxies. All right. Oh, and then you see the red colors means high fraction of blue clouds, high fraction of green valleys, high fraction of red sequence. And then you see, a behavior here as a function of stellar mass. But here in the blue cloud, there is a high fraction of blue cloud galaxies in the outskirts of the cluster. Yes, because the galaxy still didn't fill the hot gas in the cluster. It's just interacting. It is still in the tidal mass loss, but not enough to change, consistently the galaxy. And as you go to, more massive systems, you see going down in the outskirts. You don't see it. It's a little fraction. You don't see too many, blue clouds, high mass. So there is always this competition. You cannot just say it's blue cloud, green valley, red sequence. You have to remember because it goes with the stellar mass.
I can see from here, what is the scale for the radius is R200, is that it?
Yes, this is the projected radius divided by R200. Yeah, R200 is to be. Essentially because, here you go, they come with simulations. You see these lines in here? These lines in here comes from the cosmological simulation. And they tell us exactly, this region is very low in time since fall. Because from a simulation, I have that information. From the observation viewpoint, I don't have that. Right? I don't know exactly how to compute the time since fall when I see a galaxy in that location of the projected phase space. So that's why I have to rely on cosmological simulations. And then here is low value of infall time, and this is high value of infall time. And then comes, the important information I want you to focus on to show why morphology is so important. Here we brought the quenching fraction as a function of the default time. Right, so here are the center of the cluster and the outskirts of the cluster. The stars here represent the field, the percentage of the field. So let us see, again, it goes with stellar mass. Low stellar mass, you see a low quenching fraction when the galaxy is right there in the outskirts. But then when it gets to 40 years, time between fall, it goes up very steady. The same thing when you go for other stellar mass names, it's always the same. And notice there is a difference between fraction of quenching galaxies in the field where you have low density and the outskirts of the cluster, which is right here. So when you translate the quenching fraction and you measure the early type fraction, which means morphology, right? And you see a behavior which says a lot the way the galaxies are moving in the diagram. Because notice, for instance, here, this is low stellar mass B. The first part of the cluster, the outskirts of the cluster, has a higher fraction of early type galaxies compared to the field. So a fraction of those early type galaxies were quenched when they got very close to the cluster.
Sorry, I'm not sure. You have two axes there, one on the top, which refers to radius, the other on the bottom refers to time.
Yeah, well, forget about this, just our numbers. Yeah. The numbers of those regions of time changing fall. You have different numbers. 1, 2, 3, 4, 5, 6. We merged 6 and 7. Okay. And verify this. This would be 1, 2, 3, 4, 5, 6, 7.
Okay, all right.
All right, so it's just never, but forget about that. You are kind of relevant. It's just one of the things that the referee has to put in the paper. And it just completes things you did, but it doesn't mean,
Well, I already had 10 minutes to think about this.
yeah. So, but the important thing is here, right? It's time seems to go. So notice that for the low redshift, the low mass range, the fraction of ordinary galaxies is higher than in the field. The same thing when you go a little bit higher in stellar mass. But then when you move to very massive galaxies, there is no difference whatsoever. What is this telling us? When you look at the massive galaxies, when they approach the cluster, they already quench. They are elliptical galaxies already. And this is very confusing because, when you say, look at a massive galaxy, an elliptical galaxy, and I want to measure the quenchant fraction. Well, and I want to associate the quenchant fraction to the properties of the cluster, of gas in the cluster. But the thing is, when the elliptical galaxy reaches the cluster, is already elliptical. So there is a bias, there is sort of kind of primordial bias in a sense. I mean, a galaxy had already morphological type elliptical when it reached the cluster. So that gives makes a sign that you gotta be careful when you associate morphology to a quenchant fraction. There is obviously a relation, but you have to pay attention to this difference between field and the outskirts of the cluster is issue here. And notice that the field essentially it goes like this. It's the average of initial time, not even in the center, there is no difference whatsoever, which means massive elliptical galaxies, when they reach a cluster, they are already elliptical galaxies.
At least recently.
At least recently, that's right. That's right. When I say this, I'm assuming that the main sequence diagram didn't change at all from, let's say, redshift 0.5 to redshift 0.1. That's correct. Thank you. So I skip that one. The bottom line of all the discussion is morphology is a fundamental parameter of evolution, right? The tricky part is we got to be careful how we measure morphology. And let me just entertain you with this very boring question, which is the eye reliable in pattern recognition? And the answer is no. We know it is, right? We know it is. And when you look at the galaxies, this is very nearby galaxies. When you look at the elliptical and spiral, very easy. All of you can distinguish. When you go to higher and higher redshift, it becomes blurry. It's even worse than this. Look at this Stellar data. This is a slow data, which is bad data, by the way, right? It's optical. This is the Hubble data from space. Very good data. Still in the optical. And this is James Webb data in infrared. Look at the differences. When you look at the, compare first optical to optical. It's just one image which is much better resolution than the first one. And you see all the gory details. And then you ask yourself, for the eye, do you really need all of those details compared to this one? I don't think so. If you want to establish just a classification saying either is a spheroid or is a disk galaxy, you don't need that. Yes, it helps a lot to have beautiful images, to put in the newspaper, but for the point of view, morphology, not that much. The same thing when you go to the James Webb. Look at the amount of detail we see here, all these irregularities within the galaxy. And that's the question that we have to address. Do you want to carry all of those specific high resolution details into the morphology? If we do so, there's one option. You go crazy because there is no way you're going to encompass all this information in one parameter, or even just separate disks in spheroids. As I was saying in the beginning, the intent is as we move out in redshift, gets very close to the place where galaxies start forming right in the past. I want to know what is the fraction of disk galaxies at that point, because that sends me back to an epoch in the universe where I can test all these people's ideas of torque, angular momentum, creating the rotation in galaxies, And then you should have a very high fraction of this galaxy at very high redshift. But now think about, well, the only thing I want to know is either the galaxy is a spheroid or a disk. All right, just summarizing visual classification. Visual classification is great because, it's good for better recognition. The eye integrates the information and the eye gets adapted very easily. If the data is good, or if the data is bad, you look at the galaxy and say, oh, this is spiral galaxy, or this is elliptical galaxy. But remember, those things are only valid in low redshift regime, things which are very nearby. And I'll show you in a second exactly how it looks like galaxy high redshift. Weakness is subjectivity, right? If you have 5 people classificating galaxies, as they go faint, you can get very different answers for the same galaxy. Limited visual range, limited fatigue, resolution, limited scale. Limited scale means you cannot process, millions of galaxies visually, the way of doing this. So what people have been doing, in the last, let's say, 15 years, when they apply, very fancy techniques of convolutional neural network, very fancy name. But what they don't tell you is that they need a training set for the deep learning. Deep learning is great, but you need a training set. How do you do a training set? 99% of the papers so far, they do visually. Imagine to do visually when you go with a very high redshift. You will be surprised at what kind of things that you get. I'll go very briefly in describing sidewalks, the pipeline, to get the image, download the fields, fill out stamps, make image, segment image, and instruct the metrics. This is an important thing. Have an image. I don't want to do anything different. I just want to measure parameter. I want to have an information which comes from the data with no human intervention. But
So the metrics, do you choose the metrics yourself, or in some sense you let the sample decide which are, let's say, the principal vectors or whatever, the parameters that describe the minimal set of parameters that describe yours?
your questions are always anticipating my next slide.
Sorry, I'll shut up.
No, don't do it. No, actually, we have to think about these metrics because, as I said, the traditional way is measuring concentration, asymmetry, and smoothness, which are parameters that by the name, you don't have to know exactly what the equation is. It's very clear what it is, right? Concentration, how concentrated the light is. Asymmetry, if the galaxy is too asymmetric or not. And smoothness, is the galaxy distribution, the light distribution, is it smooth or not? Or is it heterogeneous? So what we did was to say, well, forget about this. Let's think about, more physical way of looking at galaxies, looking at morphology. The entropy here is not that entropy that you guys are thinking about. It's a Shannon entropy. Captures the randomness or unpredictability. It's better. In here, in the images information content, which means if you have a galaxy which is quite smooth, you can imagine where does it go? Which entropy goes there? If I have an elliptical galaxy, it should have a high or low entropy. Elliptical, low entropy, right? And the opposite for spirals, because the spirals is very irregular, H2 regions, star-forming regions in the galaxy, so the elliptical are older. This has nothing to do with age. This is morphology. It's just the way the galaxy looks like.
But usually, are they older, elliptical?
They are older, but that's kind of information that we don't want to use here. Because of age, well, that's complicated. Let me elaborate a little bit more on this. When you say age for a galaxy, you're not measuring the age that the galaxy was born, like in the case, right? Say, I'm 68, I'm 51. It says, when I was born. In the galaxy now, it tells you the last episode of star formation, because that's what dominates the spectrum. So you never measure the age of the galaxy. You measure the age of the last episode of star formation. So when in here, there is no spectroscopic information whatsoever. And we want to be that way. Right? So entropy is the first one. The Gini, well, maybe you can say better about Gini, which was a parameter from an economist in Italy, with the idea you should have a parameter which measures the inequality. We better don't measure this 50%, right? In the sense that when it goes to zero, it means the wealth of the country is completely concentrated. And when you go to one, it's spread out. So what you want is to have something very close to one in life, not for galaxies. The galaxies differentiate also. When you look at the spirals and ellipticals, they go in different ways, not as much as in a society. And the third parameter matches the gradient pattern, of an image like this. Look at the example. You have an image of a spiral galaxy like this. What you measure is for a given pixel in the image, you look at where the gradient is going. From that pixel, what is the direction that changes more, the flux at that pixel. And then you create this pattern. When you look at these two, it's like, oh, okay, I will sit higher in the center, and I will measure the opposite vectors. And I will ask, are they similar or are they different? And then I create something which is the parameter we call G2, which is it's an integration of all the asymmetric vectors. Which means, you can intuitively say, in here, you're going to have it 0, because all the vectors will just disappear, right?
Aren't you just using some saturation limit there? Because you still get an increase in the density. You still have a gradient as you go to the center of even an elliptical there, right? You are kind of saturating after some point.
You're saying here?
Yeah.
Right. Just because in here, you just cannot see the vector because it's so tiny.
Oh, you haven't really applied. Okay, all right.
Right.
So it is, there's a gradient, but it's so small that
It's so small. Yeah,
that's just scale. Okay,
right, right. It's not the gradient of the light distribution, it's because it's local, right? What we measure. Surprisingly enough, here is the ticket. This is a traditional CAD system. Concentration, you see it there's movements. And you see blue means spirals and red elliptical galaxies. Concentration works okay. Parameter A0, but these, by the way, these areas are always normalized by 1, right? The total area. So A0 is the overlap area between the two. So what you want is to have A0 very close to 0. And in this case, you see it's 0.56, 0.59. When we go to our system, A0 is always 19, 0.15, 0.95. So it separates early type galaxy from late type galaxy quite well. That's the thing that we believe, but it is a better way of establishing morphology. And notice at this point, we didn't do anything visual. It's just measuring parameters over a galaxy. All right. So as I said, people have been using the CNN, the deep learning CNN, and but they need a training set. So now we are in a position to use our metrics to come up with a way which is completely unsupervised. How do we do it? We do using this method, which is called self-organizing maps. Self-organizing maps, for those who are not familiar, this is the kind of neural network. The names change a lot, but actually there are different implementations of self-organizing maps. But essentially, we use this one subreddit which works better. That's the only reason why. Just to give you an idea how this works, you have an input layer. Input layer means all the data you have, all these metrics we have for each galaxy. And then there is no hidden layer like most CNN do. It goes, every point goes to every single narrow. I gave this talk recently in Italy, and a guy asked me, what do you mean a narrow? What is a narrow for you guys? Because you guys keep saying, well, the narrow network, what is the narrow exactly? And the narrow in this context is a mathematical condition. To make it more simply, think about decision tree. Give a lot of parameters, and then at a certain point, you've got one parameter anyway, well, based on my training set. If this parameter is higher than this, it goes to ellipticals. If it's lower than this, it goes to spirals. And you keep increasing the decision tree like this. This is a decision tree. It's kind of similar to neural network, but it works exactly the same way. So, as you can imagine, when you have just the input and you associate every point to all of the neurons, the 2D representation of the neurons, right? What Sombrero does is something like this. All the points that have metrics which are very close to each other is going to, beginning is just a square lattice. As it finds points concentrating here, or concentrating there, the metric moves, stage like this, will go in the direction, whatever is the cluster, right? If it finds a cluster in the data, of course. So this is just an example. What we did in real life was different, but it's just a, divided in 4x4. This is starting from Domingo Sanchez. This is very low redshift data. It's 650K galaxies. We select randomly 36K. And then we apply some, we measure the matrix, we apply some value, and that's what we find in the beginning. Here are the matrix, right? Entropy, G, and G2. Notice that this cluster here, this neuron here, has a large fraction of large entropy, low G, and large G2. If you go to the opposite, not like this, you have low fraction of entropy, higher G, and low G2. So these two are very opposite to each other. And this diagram shows much better. Still, if we want to show that the method works okay, we are always comparing to visual classification, but not visual classification based on 5 over 6, just a project, citizen science project called Galaxy Zoo. Thousands of people classify galaxies. But again, it works perfectly okay, but for the low redshift. So since we want to prove that the method works okay, we are comparing to Galaxy Zoo. And then as you can see, these clusters here, they separate beautifully, spirals and the legions. As in the opposite, gets very large fraction of a little small of spirals. I'll skip that one just to show the hierarchical way that we do this. This is a much more important thing. In real life, instead of doing 4x4 read, we do the 60x60. There is a way of establishing the number. But these are 3 different types of selecting what we call the 2 most prominent clusters. And here we set an accuracy of 85%. Forget about what accuracy means at this point. The important thing is how do the intention is to get the point that we have the 2 prominent clusters that separates really well early type and late type. That's what we want. So we play to see what the accuracy is for each one. And in the end, we have these 2 prominent clusters. Spirals are here, ellipticals are here. And if you look at the confusion matrix, true class versus predicted class, you see a 95% very balanced. Again, very balanced 5% and 4%. That's very good sign. It works pretty well in low redshift regime. Okay, so now we have a way setting the training set without using visual classification. It's just purely based on data. There's no intervention. There's no human intervention. I just defined here these quantities for those who are not familiar with the CNN, but not very important thing is there is this loss function here. You see, always when you have a data set, you have to get a training set and a validation set. So the training set will go there in training, and then you define what the neural network is. And then you apply that neural network for those galaxies that the training never saw. Has to be working okay, right? This function compared to training and validation is just to show this is what we expect. We train with this function, and we recover exactly the same function when we apply to galaxies that the method never saw. That's a good sign. What happens very often is that when you see the training or the validation going down, which means you're training too much, you're getting into the noise of the data, and that's not good. You cannot overtrain. You have to train properly. In a sense, training properly means the data that you train, you get the same result when you look at the validation data. Okay, up to this point, we have a new metric system, the entropy G entropy 2. It's completely unsupervised and provides with an accuracy which is very similar to what galaxies do have. And so what we are proposing here in this paper that we published in January this year is a hybrid approach, which means unsupervised plus supervised. Supervised in the sense that we get the training set that we get from the Sombrero and fit in the deep learning technique. Okay? So again, completely independent of human intervention. So we made sure that the same approach works for HST data, going to higher redshift. But obviously, as everybody's doing, then we went to chemistry. Chemistry, the cosmic assembly, near infrared spectral lens, huge. And notice that now I'm going to redshift 2.4. That's the distribution of a number of galaxies, the function of redshift that we have initially. So here's the being between 2.2 and 2.4, in beginning 0.2 to 0.4. But when you go to high redshift, now you've got to be careful. First of all, have to get a magnitude 24 for those who are familiar with 24 means incredibly faint. Well, not at this regime. 24 is okay. And stellar mass above 10 to the 9, essentially because we cannot measure reliably below 10 to the 9. And this is to redshift 2.4. When you go higher than this, I will show you in a minute. You have to go maybe to 10 to the 10 or 10 to the 10.5. Just to give you a measure, look at this. These are galaxies, redshift, low redshift regime, 0.2.4. And you may say, you can classify this visually. But when you go to the high redshift regime, you're here talking about 2.8 and 3. Look at the galaxy. How do you classify something like this? How do you classify this? So it becomes very inaccurate the way you classify galaxies. And this is fundamental. Because remember, we want to distinguish this from spheroids. Because the fraction of this is fundamental issue. It's a detail, but I want to bring that up. Most papers, what they do is they take all the data from redshift 0.2 to 3, and they run one CNN, one deep learning. Here we prove that is a wrong procedure, because actually you have to do in redshift beams. And why? Well, first of all, different redshift beams means different evolution for the galaxies. And also, for a given resolution you have, whatever data you have, resolution will go down. Your resolution will find more difficult to find galaxies at higher and higher redshift. So it's a risk just to take one single set, all the galaxies in the redshift range, the whole range, and just come up with the one deep learning. Here is just to show, this first one is singular. With fixed gear, suppose we take these two first beings in redshift, and we use the neural network with deep learning that we found in here, and apply to the others. When you apply to the others, you see the mean match goes down to 50%. 50% means random classification. You can say whatever you want, right? That's what 50% is. So that means you have to do in redshift beams. Yeah.
So let me see if I got this straight. So you get the EGG to start with the separation cluster, find the clusters of the early types and late types.
Right.
But then you have to define, and this at this point there is some very basic level of human intervention. You have to define a cut saying this cluster is early type, this cluster is late type. This is so you have in some sense you have to do this. A human has to do it.
No.
No.
There is a function that they call the elbow function.
Okay.
It goes with the coordinating delta
Okay.
You
can also have that also.
Yeah. Essentially what you do is, remember when you saw, it's gonna take a while to get there. This one.
Yeah, this one.
Those are a lot of clusters.
Yeah.
There is a function which measures the RMS of all the clusters in here. When you plot the RMS versus the number of structures you see in there, you say, well, what is the best number? 2, 3, how many clusters do you have in there? You find one measuring the largest difference in RMS, the highest jump, and the highest jump goes from 1 to 2. And then after 2, 3, 4, it changes just a little bit. So you are in the noise regime of the data. So that comes naturally from the data as well.
My question is really this, the precise locus of those two clusters is different for each redshift bin.
It is. Yeah, it is. So that's why you have to do for every redshift to be. You cannot just assume one single one for the whole of it. Yeah. All right, I was talking about this. Yeah, you can see how difficult it is. This is good detail. That's a big. These are the measurements we did. Blue for the fraction of this, and red for the fraction of this rocks. All the points are measured, here red. People who did visually. And as you can see, visually, they always underestimate the fraction of the steroids. And they are okay. If you say that we're right. Up redshift 1.7, that's okay. But then when you go further than this, they underestimate the fraction of this tremendously. So this is what we are saying here, and especially Gonzalez in 2011 measured these points here. Fortunately, he is in our paper as well, so he can say that he can correct himself and not be right. But that's the important thing. Fraction of this galaxy is a functioning redshift. So and we show that our method, it works pretty nicely. Much more than this, and that's a kind of product that we find, which was very interesting. Here we see, each panel means a redshift range, low redshift for 2.4 up to 2.4 and 2.2 and 2.4. But notice here we have 3.4 gigayears of back time, and here we are talking about 11.5 gigayears in the back time. Right? The very interesting result we found, it's not there in the literature, and we hope you are right, is that blue means this, and red means steroids. And as you can see, the steroids at the high redshift regime, they're on top of each other. Here, I'm plotting specific star formation rate, which is star formation rate divided by stellar mass. Why divided by stellar mass? Because we know that all the parameters we measure in galaxy evolution, they go with stellar mass. I don't want to bring stellar mass to the, the distribution. That's why
I can see from here, but they are all star forming. I mean, I don't see the number for star formation rate there.
No.
In the highest redshift beam.
Well, this they are. Yeah,
They are all very much star forming in that redshift.
yeah, they are star forming.
As they should know.
As they should.
Yeah.
As they should. But notice, the thing is not the disks. The thing is the steroids.
Yeah.
Because the steroids at the high redshift, they are producing stars in the same way as the spiders. But as you go down in redshift, there's this bimodal distribution in the steroids, which means there are two kinds of steroids that people didn't know about. And that comes just purely from the method we use. Because remember, the specific star formation rate that we are using here has not, it was independently measured from the data. It has nothing to do with the morphology. That's the beauty of the result. So there is a meaning of what this bipodality is. And now we are investigating. We are looking into the detail exactly what the difference is. Are those types of steroids one more compact than the other? We don't know. This is the main sequence diagram as I showed there in the beginning. But this is just looking at the steroids. Forget about the disk. That's why you have the log saturation rate quite low. The important thing here is probably connected to these two families of steroids is the fact that they follow the main sequence relation as we find in low redshift. Up to redshift 1.5. Because after that, what we see is the second family gets one single value of its star formation rate. It doesn't change more, with the stellar mass. although the first component looks like it keeps increasing. Higher information rate, higher stellar mass, but not for the second component. Second component basically has one single bad starvation rate. This is very interesting. I say this is very interesting. It's just the same thing to say we don't know exactly what it is, but at least we think we have something in hands. Now there are all kinds of things that we can study with us. In particular, I want to call your attention to this question of in situ and in situ. When you discipline the knowledge that changed over the years, when you say that a galaxy interacts with another galaxy, and then brings a massive galaxy swallow a low mass galaxy, right? You may say this is galaxy merge, or you can call it this massive galaxy. It's an inside out, growth, or you can say that there's a fraction of in situ and ex situ for each galaxy. So the stars are forming, in the beginning with the galaxy, it's in situ. Whatever comes afterwards is ex situ. And this is probably changing with the redshift, because it depends on the fraction of merger as a function of redshift. So that's a crucial information. And that's why we're investigating this. And at this point, we have to rely on what cosmological simulations tell us, because we have no idea exactly how to measure properly what is the fraction of in situ and ex situ. So what we are doing is we go to simulations, and the simulations say, well, if you go there and you measure, for instance, the size of the galaxy versus stellar mass, you should see a sort of a relation which comes from the simulation. And that's what we're doing. So let's see if we find something similar. Which doesn't mean that we are understanding exactly what it is, but at least we are on the right path. Okay, this is diving into the primordial area. Now we go to redshift 8. There are certain things here which are important to remind. Well, first is the look back value versus redshift, right? It goes very fast and goes slow. All right. But there's something more important here, which is the way we measure things. Because think about it. When you point a telescope, you put a different filter. Galaxies at different redshift, you're going to prove different parts of the spectral energy distribution for different redshifts. That's not what you want, right? You want to measure always the same part of the spectrum for every galaxy, regardless of what redshift it is. That's why in this plot they show the curves are for different filters. And you see filter F115W, blah, 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 for a given redshift beam. So this is the rest wavelength, and this is the redshift. So if you want to measure galaxies, let's say up redshift 1, you should use this filter over here. It's because it covers the optical wavelength. That's what it's called, the optical wavelength means on this area, shaded area. So that's a very proper way of guaranteeing that you are always proving the same part of the stellar population in that galaxy, whatever that is. That's a very crucial thing to do. Okay, now I bring that up because I brought this text because I find this beautiful. People in this book of 1980s brings that discussion of rotation of galaxies. He wasn't the first, to come up with a mechanism to explain how do you have rotations in galaxies. And then, it's a very simplistic thing because, we have just torques is the coordinated angular momentum with time. So you have the blobs, even before they made galaxies, you have the blobs interacting and they make torque. And then that goes, this together with the orbital energy they have, that goes internal to the galaxies. And, it creates disks. Even for the blobs, neutral hydrogen before they made galaxies. That's a very interesting approach, did by Peoples. And I think with these, but Peoples, it doesn't come with a prediction for the fraction of these galaxies. And yes, he couldn't do it because he had no way of estimating the fraction. You have to know exactly what the mass distribution is inside the galaxy and what is the distribution of the blobs you have around before they make galaxies. We will know this when you have the square kilometer array. Remember, when we talk about James Webb will go up to the point that we have galaxies. So that's what James Webb can measure. This would be roughly redshift of 20. At redshift of 20, it means SPA will prove to redshift 100. Think about it. Redshift 100 means 16 million years after recombination. it's always nice, to think about and have these numbers in mind, to see exactly how important they are. So again, look at our measurements we did. I'm just repeating the figure that I told before. And this is a recent paper showing James Webb data. It's one of the best papers because they take care of all the details. And look at these two things here, because they measure the morphology fraction. The blue ones are disks, and the disks are slightly lower than 0.6, which is precisely what we find here in the same redshift regime. And their methods are completely different from ours. And we use HST data. They use James Webb data. And still we find the same thing. The same thing for steroids. It's slightly above 0.2. Here, slightly above 0.2. So it's I would call it insanely similar. That's another paper, just a completely different method. We call it contrasted learning framework, and which brings an issue. It's very complex. The contrastive method works like this. Take one galaxy and they use what they call augmented data. You take a galaxy and you rotate it. You squeeze it in the scale of the galaxy. You apply different ways. It's always the same galaxy, right? You are just playing with the way that the galaxy shows up to you. And in the end, what you want is to compare all the pairs of galaxies that you created, so to speak. And the neural network has to be able to identify that these galaxies are the same. Because you just change, the scale, rotation, and all that. And rotation doesn't change the morphology of the galaxy. So it shouldn't. Really. This is a very interesting paper. And the most important result they have is they say there's no way we can distinguish between this galaxy or an elliptical prolate. Prolate is just like a cigar. If it's a cigar, it's not a disc. But it's a cigar, and if you have this populating the same part of the diagram as they show of the discs, you don't know how to compare, you don't know how to distinguish them. And that can damage a lot the fraction of this. They estimate that people are overestimating the fraction of this by a factor of 5, which is a lot. Sure, you have to believe in whatever they come up with. It's a very, complex kind of methodology. We are not going to use that one, not for now, at least. That's another, aspect of just to finish, the presentation. When we look at these papers based on the James Webb data, they call it cosmic morning, noon, and afternoon. I don't want to say anything bad about them, but they said it's kind of meaningless if you think about it. It's just trying to translate 8 to 4 means 1 gigayear. 4 to 1.5 means 2.8. 1.5.6 is 4.5 gigayears. That's what it is. There's no thing like that using. The important thing is when you look at it, this is a function. Morphology fraction is a function of stellar mass. Again, right? Look at this one here because it goes by the super gene that we are proving. So, right? So what we see, for steroids. Yeah, now we're comparing the steroids. As you go higher redshift to lower redshift, you see the fraction increasing of these steroids. The mass have more high mass steroids nearby, which is precisely what we're seeing here. Look at the bit of the red distribution. It's almost close to 10. As you move down to redshift, it's 10.5 and 10.7. Okay, the steroids are increasing. Again, is there anything new on that? No, people have found this before. But the interesting thing is that we are now comparing HST data with James Webb data, which is far much better, and completely different method, and we find exactly the same kind of behavior. So this is very interesting. And on top of this, we have this bimodality, quite a lot of bimodality in the steroid distribution of specific information rate. That's a summary, of what I said before, but I'll just leave it there. I'm not going to repeat it. Thank you.
So, yes, go ahead. And then the other questions.
Has to be.
So in some sense, at high redshifts, the morphology versus star formation there's no distinction. They're all star forming. There's no significant difference between the populations. This only happens at lower redshift when having let's see, becoming elliptical is the only pathway to quenching star formation, because all the other the spirals, they typically end up having some star formation. So the only path to stop that. Okay,
That's correct.
okay. So this is
Maybe I would say differently, but you're absolutely right.
so in this sense that there is a pathway for galaxy evolution to kind of create another population which is connected to morphology. So that's it. So you have an idea for the physical mechanisms that are, I mean, so it's a necessary condition to quench star formation to become more spherical. I mean, what is how do you envision that this has to be the only pathway, right?
Notice that at a certain point, in the beginning, I spoke about field versus cluster.
Right.
At a certain point, I disregarded that evidence. And why? Because essentially, after redshift 0.5, I have no idea what the galaxies are. Because it's very difficult to identify clusters. You don't have any complete sample of clusters that redshift higher than 0.5. You have specific works have done, cluster here and cluster there. You don't have exactly that kind of thing. And you would need to know this to see exactly. Remember I said in the beginning, an elliptical galaxy coming from the field, when it reaches the cluster, if it's an elliptical galaxy and you go there and you measure the fraction of quenching, it is already quenched. There's nothing else to quench. There's no gas left to quench. So an elliptical galaxy in the outskirts of a cluster or in the field, they will look to you exactly the same, regardless if you look at morphology or stellar population. So that's a confusing thing. Moving out the redshift, 1, 2, 3, you have no idea. You expect that when you look at a very massive galaxy, you must be proving something at the center of a cluster. Because we know, the segregation that we have in mass and luminosity of galaxies in the nearby universe. But, we got to be careful. We cannot project too much of what we know in the low redshift or the high redshift regime.
But it has to be so sense connected to angular momentum. And this is kind of what you're hinting at the end of your talk there, right?
That's correct.
So, when we were looking at the spin of halos, of subhalos in simulations, we observed that there was something which was happening, which is when you have subhalos, which we call splashbacks, so they are crossing the main halo, and you look at their spin, you realize that they lost a lot of the spin when they crossed the halo because of stripping and everything else. So for sure, being or not being in a halo makes all the difference for a subhalo in terms of angular momentum.
That's right.
So in some sense, you have to find out a way to measure the angular momentum of these galaxies at high redshifts, because this is part of the answer that you're searching for, right? So is there a way to know the angular momentum of high redshift galaxies? I mean, this observation is super hard, right? But is there another way?
Let me tell you this. Just a month ago, I was in Italy. I gave this talk, and afterwards, a collaborator of mine, I have to show you something. And he showed me a spectrum of a galaxy at redshift 3.4. It's a beautiful spectrum. It's a synchronized order of 40. This is redshift 3.4, but this is it's James Webb data. Right? And with that kind of spectrum, for instance, we can measure metallicity quite well. And that's a beautiful thing because metallicity is around -0.6. Because for those who are not familiar with these numbers, 0 means solar metallicity, right? We call them above 0, more metal rich systems, and less metal, more metal poor below 0. But it means redshift 3.4, it's very close already. It's just 1.5 gigayears from the combination epoch, say, right? So it means the enrichment is going pretty fast. When you look at the spectrum like this, the spectrum, you cannot observe any rotation with it. Right? We are not at that point. And I don't think we're gonna do with the James Webb data. You know, they don't have the resolution for that. This is going to be done with the huge telescope like GMT, TMT, ELT, and especially those who have infrared spectroscopy, because you've got to have infrared spectroscopy, right? All of these things we see at a very high redshift, the peak of the emission is in ultraviolet. Ultraviolet, you know, make the figures. Ultraviolet means around 2,500 angstroms. Multiply this by 5, by 10, which is redshift 9 plus 1, the scaling factor, and you go to the infrared energy. So I think we'll have to wait more than 10 years or so to be able to measure station velocity, unless somebody comes out with the data that they can prove they can do it. I don't think they do, because you know, the spectral resolution of the spectrum is not good enough. It is good enough for spectral fitting, but not for measuring in rotation velocity.
Maybe I can jump on this because, yeah, you said, of course, you analyze morphology because it's probably the easiest thing to measure site of, you know. But chemical composition. Yeah, I wanted to know what was the information you can get from chemical composition. Basically, lower chemical composition means more negative metallicity means more primordial, no? Because you use that time to build up the elements.
At this point, well, let me put it like this. I disagree that it's easier to measure morphology.
Okay.
I think we just have the data to do it, but not easier, but the data is there. As far as the spectroscopy, for instance, this collaborator of mine, they collected from James Webb, they collected 10 galaxies between redshift 3 and 4. That's it. So you cannot say much about the, you know, chemical evolution. What you can say though, it doesn't matter much how, you know, negative you go with the list, you get closer and closer to the primordial value. First of all, because we don't know exactly what the primordial value is. Right? We don't know if there's a population 3, for instance, you know, polluting the media, you know, a redshift above 10. But the point is, just the fact that 1.5 giga-years from the recombination epoch, you are already finding things that are at metallicity minus 1.6. If you have a larger sample, this is just one object, but if you have a larger sample, you can guess if you need or not population 3 stars. That's far much more important than finding, you know, the lowest possible metallicity, you know, that, even because when you go to spectral fitting, then you bring all the, you know, devil start playing, it's very difficult to measure. But anyway, that's my answer to your question. First of all, it's not singular, just we have the data, the morphology, and the spectroscopy. It's going to be tough to get a larger sample and come up with a prediction. Remember, all the discussions of measuring metallicity is a big discussion in the universe nearby. You have 2 different groups, Gustavo Brusual, one group, Brusual and Chabot, and you know, Pastek and his group. They have different approach because one is theoretical and the other one is observation, observe stars. And they have completely different, you know, measurements for metallicity for the same galaxies, same data. So it is something that we don't even know how to do with low redshift.
So you don't even know how well it correlates with star formation activity.
Not really. Not really. Star formation is another thing you showed, but I didn't mention anything at all, but think about it. The diagram that I showed is star formation of these asteroids is around 1 solar mass per year. Sounds like nothing, right? But when you integrate over 10 to the 9 years, that's a lot. Makes a galaxy, star formation like this. But it's a hell to measure star formation rate. Because star formation rate is like suppose you have you know, the amount of mass that's created in a galaxy as a function of time. The star formation rate is the derivative of that function. How do you measure? So you have to get the stars which are forming right away at that time. Because if you go to the low mass stars, which evolve over, you know, several giga-years, you're not going to measure the proper star formation rate. That's why they measure star formation rate in UV, right? Measuring any other wavelength, because we want to catch the stars when they are created.
Okay, before we split for lunch, remember we have scheduled the next meeting for August 16th. And before we split later today, we have to find the speakers for that. We had already a couple of volunteers that I will remind you later. But okay, last call question to Reinaldo. Going once. Twice. Okay, there are sandwiches hopefully waiting for us downstairs.
All right.
Thank you. Sorry, don't forget, pay for the sandwiches, those who are not from IFP need to sign this, so we can get the money from the benefits to buy the sandwiches. You know. So,
Eu, né?
let's look at that. Your DD.
Prestado.
Eu usava isso Ah, os dados não, mas você já sabe, né, os dados, né? Eu preencho também os dados.
Agora, eu acho que o pouco tempo de uma por essa tarde, não tem tempo no sanduíche. Vai, deixa eu assinar isso. Se o nome CPS, só assinar.